Hello everybody, my name is Yuval Amit, and I'm going to be doing a presentation on Alan Hatcher's topology of numbers and Lagrange's continued fraction theorem. I apologize, I've become a little sick, so yeah, I have to do this online presentation, and my mentor is Connor Lockhart. So yeah, let's get going. So first we're going to talk about something called the fairy diagram. This is kind of the main focus of Hatcher's book. It looks like kind of this circle diagram with all these kind of circumlinear triangles in it. And we label each vertex with a number. And so here's how it goes. And so here I have a couple of them shown. So on the left and the right, we have 1, 0 and 0, 1. And that's just kind of how it starts. And then we're going to apply something called the median rule for kind of the center of these triangles, where if we have edges a over b and c over d, the edge in between them will be a plus c over b plus d. It's like kind of badly adding fractions. And we see that kind of we do this again for 1 over 2, and we just can keep repeating this process. And when going down, we just negate the number that kind of matches it on the top. So we see this is negative 1 over 1, and this is 1 over 1. And so, if we keep going, we get something that looks like this. And of course, this isn't the full thing either, because it keeps going infinitely deep. And so we've got some pretty cool theorems about it, and there's the median rule just to remember. Um, so the first theorem is that there exists an edge in the fairy diagram with endpoints a over b and c over d if and only if the determinant of like this matrix a, b, c, d is plus or minus 1, which is pretty powerful, and it's really interesting. And I don't have time to go into these theorems, but I can talk about them later. And then a corollary of that is that every fraction produced by the median rule will automatically be in reduced form, and that's kind of because of the GCD. It's a corollary. And then finally, every fully reduced fraction occurs as the label for some vertex on the fairy diagram. So since it kind of goes infinitely deep, we're actually going to get every single fully reduced fraction. So yeah, let's move on to something called continued fractions. These are pretty simple. It's basically just kind of these iterated fractions where 1 is always the numerator. So we have like 4 plus 1 over 2 plus 1 over 3 plus 1 over 7. And so this one evaluates to like 226 over 51. And we have a notation for it that looks like this, where kind of the constant number at the beginning has a semicolon in front of it, and then it's followed by 2 comma 3 comma 7. Um, and then so this is just generally a finite continued fraction, where we have finitely many things in the denominators. But of course, we can also have an infinite continued fraction where we just keep having things in the denominator. And what's nice is that these will converge. And actually, we have these things called convergence, which is just the finite bits of a continued fraction. We start with a naught, and then we go to a naught, a1, and then a naught, a1, a2, and so on. So yeah, let's move on to another thing really quick, called the triangular strip, where we have this continued fraction 3, 2, 4, and we build this kind of strip by basically doing these fans of, we fan 3 times because of this 3, and then we fan twice because of the 2, and then we fan 4 times because of the 4. And the way we label each edge is by the median rule. So the median of 1 over 0 and 0 over 1 will be 1 over 1. And then the median of these two will be that, and the median of these two will be that, and then the median of these two will be that. And that kind of just keeps going. Now, what's nice actually is that these labels at the corners are actually the convergence. And we see that this number at the end is exactly what this continued fraction evaluates to. So what's nice is that we can actually show this kind of diagonal pattern on the fairy diagram. If we were to label each of these numbers on the fairy diagram, it would look like this, and this is for 3 over 8. And we see this kind of zigzag pattern to get to our number, and this is actually always going to happen. The convergence of a continued fraction are the vertices of a zigzag path along the fairy diagram. And so that leads us to another theorem that for every infinite continued fraction, the convergence converge to a unique limit, and additionally, every irrational number has a unique continued fraction representation. So yeah, so basically every single infinite continued fraction will converge to a unique irrational number, and every irrational number has a unique continued fraction representation, which is really nice. So then we have something called periodic continued fractions, and these are basically continued fractions that look like this. It's pretty simple. They just, after a certain point, they just start to repeat. So this, after we get to AK, it repeats again. So we label it like this with a bar over those numbers in the continued fraction notation. And then we can also have eventually periodic continued fractions, which only start to repeat after a certain point. So we'll do a quick example with evaluating this periodic continued fraction. It's pretty clearly periodic because it's just, a bunch of ones. Um, and so the way we evaluate something like this is we say, okay, this thing at the bottom, well, that's a. So we can say that this is 1 plus 1 over a. And then if we solve for a, we're going to get this quadratic, which has solution 1 plus root 5 over 2. And you'll note, the quadratic formula, it does give us a negative number. But we don't want a negative number because obviously this thing doesn't converge to something negative. So basically we just ignore that. There's some details to it, but for now, just kind of ignore it. Which is, that's pretty cool that this thing converges to the golden ratio. So the question is, will we always get a number of the form a plus b root c, with c being a non-square? Because we noticed that, we evaluated a periodic continued fraction, and we got what's called a quadratic irrational. And so that is an astounding yes. That is Lagrange's theorem, which is what we will be proving. That an irrational number has a periodic or eventually periodic continued fraction representation if and only if it's a quadratic irrational. Unfortunately, I don't have time to prove both ways of this theorem. One way is kind of easy; it's easier, and one way is harder. And so we, of course, are going to be doing the harder one. The easy one is proving that you can go from a periodic fraction to a quadratic irrational, basically just what we did here. So we're going to be focusing on, given a quadratic irrational, prove that it has a unique periodic continued fraction representation. So to do that, we're going to be focusing on something called the topograph, where, so first we're going to focus on quadratic forms. So a quadratic form is basically just, pretty simple. It's a function of two variables that is just ax squared plus bxy plus cy squared. Where a, b, c are integers, and they're not all zero because we can't just have zero. And these can actually be simplified a little bit. We can using some simplification processes, we can just assume that a, b, and c are coprime, and x and y are also coprime and both positive. So that is going to be major assumptions that we're going to be making, because kind of any quadratic form can basically just be simplified to that. So yeah. So this is the topograph. You can see the way it works is we have our fairy diagram, and what we do is we put a point in the center of each of these circumlinear triangles, if you remember, and then from each point we kind of stem out three branches, and then this branch will stem out three more times, so it just keeps branching like that. And what's really nice is we have these regions, and each region is adjacent to a vertex. And only one vertex. And so we can label each region with the quadratic form applied to that vertex. So if we do x squared plus y squared, for example, then we get this, where we took like 1 over 0, we did q of 1 comma 0, and we got 1. And then we did q of 1 comma 1, and we got 2. And so this is actually really important. And there's a nice rule about it called the arithmetic progression rule, which says that for a region that looks like this in the topograph, where we have like kind of one number and then two numbers and then one number, there's a nice rule that says it has to have an arithmetic progression. So p comma q plus r comma s will form an arithmetic progression. And because of that, if you have three adjacent regions, that will basically define the rest of the topograph, which is really nice. And so now we're going to get into periodicity. We'll notice basically that for some quadratic forms, for example, x squared minus 2y squared, our topograph has this periodic separator line, where everything on the left is positive and everything on the right is negative, or it could be vice versa. And furthermore, everything along this strip is actually periodic, like 1, 2, 1, 2, 1. And so that's really powerful. And so the way we can kind of work with this is we're going to basically build the separator line by, we start with q of 1 over 0, 0 over 1, and 1, 1. And so we have this horizontal line, and on the top we're going to put a positive number, and on the bottom we're going to put, basically the top has positive numbers, and the bottom has negative numbers. And so the way it works is once we have these three numbers, we're basically just going to apply the arithmetic progression rule. So you see here we have -2, and then 1 and -1 make 0. So here we should have +2, because we have -2, 0, +2. And then we have 1 here, and then 2 and negative 1 make 1. So next up we should have a 1, so it should again be at the top because it's positive. And then this can keep going. We have 2 and 1 and negative 1, that's 0. So here we should have negative 2. And then this basically just keeps going. And this also extends in both directions, actually. And we notice periodicity, right? This is basically kind of a periodic kind of growth. So what we can do is actually we can embed a triangular strip on top of it, where it kind of goes down to a negative number anytime there's a negative number, and then fans up to a positive. And so we basically have this fanning, um, and we notice that this triangular strip also has periodicity. Right here, there's just 1 at the beginning, but then there's 2, and then 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 2. And so we can take this triangular strip, and like we kind of saw earlier, we can uh, take this periodic, we can find the corresponding periodic continued fraction. This is something I would have gone into a little bit deeper if I had time to show the other side of the proof, but basically we can always go from a triangular strip to a periodic continued fraction. And this one evaluates to the square root of 2. So basically we took this quadratic irrational and we associated it to the square root of 2. And that's kind of our main focus. We want to take these quadratic irrationals and we want to see if we can associate all of them to we take all these quadratic forms and we want to see if we can associate them to quadratic irrationals. And then just to show, this also works for eventually periodic continued fractions. Like here, it doesn't start off periodic, but then it just kind of becomes periodic after a certain number of steps. And so that's just to show that it's not only going to work for just immediately periodic continued fractions. So now we're going to get into something called hyperbolic forms, which some of you may also know as indefinite forms, but that's not that important. So basically, hyperbolic forms are defined as quadratic forms that take on both positive and negative values, but not 0, and that's important. And there's actually a really nice theorem that I proved at first in this presentation, but I don't have time now, that basically the topograph of a hyperbolic form will always have a single periodic separator line. And if we remember, from single periodic separator lines, we're able to kind of have that periodicity and find the associated quadratic irrational. And kind of a nice way to show this is that since a hyperbolic form always has a positive and negative values, there has to be like kind of this region where one region is positive and one region is negative. And then if we move on from them, if we stem away from them in the topograph, well, this thing is either going to be positive or negative, and depending on which one it is, we can just define, we can, put the periodic separator line in that direction. And so this is just a nice way of showing how there will always be a periodic separator line. Well, this doesn't show periodicity, but it does show that there will be a separator line. And so now we can finally get into the proof of Lagrange's theorem. So we're going to take a quadratic form, so a and b will be rational, and n will be a positive integer that's not a perfect square. And so we're going to take, alpha equals a plus b root n. That's a quadratic irrational. And it's a root of this quadratic function. It's not a quadratic form, but it's just, z squared minus 2az plus a squared minus b squared n. And so, it's a root of that. And since all the coefficients of this are rational, we can just multiply by a number to make it in this form, az squared plus bz plus c. Where a, b, and c are all integers, and note that a will be a positive integer. And that's something we can do because they're all rational. So we can associate this kind of quadratic function to this quadratic form. They're basically, we can determine this one from that one. And so this quadratic form, based on what these numbers are, we know what they are, it actually has 2 properties. One, the quadratic form will always take on negative values between the roots and positive values away from them. And we can see them because of this, right? When we're between alpha and the conjugate of alpha, which, because it's a quadratic irrational, we know that between them it has to be negative and away from them it has to be positive. And furthermore, there is no 0 on this, or I guess there's no integer 0 on this quadratic form. Because if there was, then we would basically have another non-irrational root to this quadratic function, which we know there isn't, right? Because it only has 2 roots, and it's these quadratic rationals. And so because of that, this is a hyperbolic form. We went from a quadratic irrational to a hyperbolic form. And because it's a hyperbolic form, it has a periodic separator line, which was the previous theorem. And because it has a periodic separator line, we can find the associated periodic continued fraction. So yeah, I think it's really great proof, and that just about wraps it up. Thanks for listening. I can't really answer questions, unfortunately, but I hope you guys enjoyed. Thanks.